course we could change that, but there's no way can we do on Thursday after class because some people don't show up. Go and play with that. Okay, anyway, we'll see. So we're still sort of randomly taking a random walk through this first set of notes called lecture notes number 1 on Lyapunov functions. I'm just sort of bouncing back and forth through this. And I think last lecture was a bit of a shock to you. I mean, so this is a Markov chain provided n is IID, independent, identically distributed. And I told you I was going to, use some abstract notation, and I didn't lie. So when I write, if I have a function, and so x is an RD. When I write PV of x, I always mean that V is a mapping from the state space to the reals. So maybe, sometimes it'd be complex numbers if we're talking about spectrum like we did last time, but we're not going to talk about spectrum again. I mean, it's just fun to see that these concepts carry over to infinite, settings, but it's not very important in this course. When I write PV of x, I mean that V is a function in the state space, usually taking real values. If I write V, usually it's non-negative valued. And I always mean the expectation of the function one step in the future, given that at time t, I'm in state x. So that is the definition. Now, yes, for a finite state space Markov chain, it's matrix vector multiplication. Okay? But that's just a consistent fact. All right? So I'm basically just keeping this notation because that's 1, 2 symbols, because I'll usually leave out the x. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 symbols. And if we had to write all that out, every time we wrote down a dynamic programming equation or anything, we would go nuts. I would get carpal tunnel syndrome. So you have to memorize this. And I I feel like an idiot, but this is what stops most students when they take this course. Believe it or not, they refuse to learn this definition. Because just from experience from teaching this course for 15 years, that's one thing, is what sort of separates the winners and losers. Whether you will memorize this notation or not. Okay. Okay, so we played around with the linear case, and we found we could solve this Poisson's equation. Well, I'll write inequality. If this cost function C is quadratic, we can find a quadratic function that solves this, provided the natural stability assumptions hold. So I won't review all of that, but we know that stability of this stochastic system is going to be equivalent to stability of the noise-free system. And you should know what that means for basically eigenvalues of f or determine that. And so we can solve this in that special case. And we can solve it with equality instead of inequality. And anyway, so there's that. So I want to give you a hard result that this does imply something. I told you it's as simple as the fundamental theorem of calculus exercise we did before. So I'll also write So before we had this, what I call a differential generator in the continuous time deterministic case, and I told you if dv was less than or equal to minus c plus a constant, that implied all sorts of things. It implied the average cost was bounded. And if you go back to your notes, you'll see the proof was completely trivial. It was a fundamental theorem of calculus. It was the fact that once you interpret this as a derivative, you just integrate both sides and you get a bound. Okay? Well, it turns out it's exactly the same in the stochastic case. There's sort of a fundamental theorem of calculus, and you get bounds on average cost without any thinking at all. It's mindless. So I'll explain that today. So I'll go through another example and give you a theorem. And I think that's enough for 45 minutes. All right. Okay, so here's another example that's like one of the canonical examples of Markov chains. So it's called the reflected random walk because without the max here, without the plus is the same as saying max, you know, the positive part. Okay. So without the plus, this is called a random walk, that you're basically just adding on IID increments to a variable. It's a model of the income from a casino, you know, there. Where NT would have positive mean, and they're making more and more and more money as people gamble. So it's, you know, it's usually motivated by gambling, but it's also a model for a Q. So if in the typical cases, this is you know, it could be a reward. I mean I'll put a question mark there. I mean, the plus sign doesn't make as much sense. Basically, once it hits 0, it's out of assets, it's broke, it closes out, which isn't likely to happen. You know, so it's more traditionally the buffer size of a cube. Okay, and then in that case, you always assume that the mean of n is negative. The common notation is that it's minus delta, just to emphasize. Like delta is the drift downwards. Okay.
What's the buffer size of a cube there?
That's what OXT, I've got a buffer. I've got packets coming into a computer, and they have to be stored up as they're processed.
Okay.
Yeah.
So buffer size
yeah.
The number of packets.
Yeah, so XT will be the number of packets waiting, you know, for processing. Okay, so that's the drift downwards. So imagine, so here's the interpretation. Let's just do a thought experiment. I want you all to do a simulation in your brains. So I start off the initial condition way out there at some enormous value. Okay, because remember, I'm not restricting my buffers, if you like, to be, you know, finite. This is just to think about it. What would happen after 10,000 time steps? What's that? Well, 10,000 is not very large if you start off at 10 to the 10th. You know what I mean? So let's wait 10,000 seconds. What happens? I mean, you've got. It's not very likely that plus is going to kick in, right? All right. So basically, it's basically unreflected. Right, because if you don't have the plus sign there, all you're doing is adding on additional increments. You've got the initial condition, plus n1, plus n2, plus n3. Because, you know, if you start this large and, you know, say t is less than 10 cubed, it's really, really unlikely that plus will kick in. So let's just assume the ends are bounded or something, so it just doesn't happen. So what's the sum of a bunch of independent random variables? Well, that's the second question, absolutely. So it could be approximated by a normal, but what about even a simpler approximation?
Probably around 0.
Well, except, yeah. I'm taking delta to be 1. Yeah. And so the mean is actually -1. So you get a puppy, you get a puppy. This can be approximated in some sense by x0 minus t times delta, and again, we took delta to equal 1. And then you get a puppy plus square root of t times an n0 sigma squared n in a variable, approximately in distribution. All right, because we know that basically there's a law of large numbers. If you take a sum of independent random variables and divide by t, they converge to the mean. 1 second. And then if you subtract off the mean and then normalize in a different way, you get a correction term, which is your suggestion. Yeah.
So this process never decreases?
No, it was decreasing, right? Minus t. Remember, the mean of n is negative.
And then when you take the max of 0 to negative?
X is positive. X is positive, yeah. Like if it's buffer size, yeah. But I'm just saying if we start with a really large initial condition, you know, and we don't take t too large, we're not going to see, X won't get negative.
Okay.
You know? I mean, take a look at it. I said delta's 1. There's t around 1,000 maybe. What did I say? T was, 10 at the 1,000. Okay, so we said was 10 to the 10th. That's just 10 to the 3. The square root of 10 to the 3 isn't very big. You know. So the likelihood is an approximation. The likelihood that this is negative is really unlikely. So the chance of this plus kicking in is very, 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 very small. We can work out a probability. All right. Now, so we can plot this. And unfortunately, I can't fit in the blackboard. Because if that's 10 to the 10th, you know, I don't know where I am. Okay, but I guess I've obviously compressed space to get this in the blackboard, and I'll maybe have to compress time as well. All right, and it has a slope of 1, and this thing is insignificant compared to this for large t. And so what does it look like? You know, there's some chattering around that, but it just, from this time scale, it would look like that. Remember, this is 10. This is 10 to the 10th. These little fluctuations are just going to be. You won't be able to see them. That's what you actually see. If you try to simulate this with a very, very large initial condition, it would just look like a deterministic fluid model. Where, you know, a bucket where water drains out at rate 1, and then once the bucket's empty, it stays empty. That's what it would look like. You know, that's an absurd situation. It doesn't make physical sense, but it's a first shot intuition about how the dynamics are. They're really boring. Queuing models are just boring buckets. You know, when you look at the fine-grained detail, they look scary. And then when you think about the coarse dynamics, it's just a drip, 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 plus a bit of Gaussian perturbation on top. That's what they sort of look like. All right? So that's this is how you should look at these problems. Just try to get some coarse intuition and then refine it. All right? Yeah.
I guess maybe just quickly explain how the radical T came out sounded like the same as that.
Well, the central limit theorem. So we know that 1 over T sum 1 to T of NT goes to minus delta almost surely. That's the LLN, right? And then we have the CLT that if you take the 1 over square root of T, or N, I mean, and you take the sum from 1 over N, you take NT and you subtract off its mean. And if that means adding delta, you know, because the mean is minus delta, so if I subtract the mean, I'm adding delta. That converges in distribution to a Gaussian random variable with mean 0 and variance, which is the variance of n. Okay. Oops. And if you go and unscramble those two things, you get that. Yeah.
Yeah. So I mean, I don't get why is the slope minus delta? I mean, like for large T, I can see the like.
That's what I'm saying. Large T. I said T was 1,000, right?
Okay, but
yeah.
you do the.
Well, look, if that's 10 to the 10th, and we're saying the slope is 1, then that is about 10 to the 10th. That point there is very closely x0. I mean, 10 to the, what is it again? It's, what's x0? It's approximately x0 plus or minus something on the order of the square root of x0.
Yeah, then
you know, because there is some, you know, but I can't see, on a plot like this, something on the order of square root of x0 is insignificant compared to 10 to the 10th. 10 to the 5th is insignificant compared to the 10 to the 10th. You don't like that? Yeah.
Then it will flatten out, right?
And this time scale be 0. You won't see a thing. If we zoom in, we'll see something very different. This is if x0 is 10 to the 10th. If okay, if it's x0 is equal to 10, you will see, you know, something like that fluid model behavior, because there is still negative drift, but 10 isn't very big. It's not big enough for either the law of large numbers or the central limit theorem to really be very meaningful. And so, I mean, I can't, it's hard to draw things in discrete time, right? So I'll just interpolate, so it'll look like this, you know, and then it'll continue to hit the origin. You know, this plus will hit it all the time because the negative mean is going to keep forcing down towards the origin. So when you look at it microscopically like this, it's how that intuition goes.
Is negative delta?
That was our assumption right there, that the expectation, the increment was negative. That was our definition. I made because that's the common notation in this field. When you look at networks, the delta, it's called delta because it's the drift. Minus delta is the drift. Yeah? You happy? Okay. So you do this and you say, well, shit, obviously it's stable if delta is positive. You know, and then you can go through and take out your Lyapunov machinery and stuff. And it's really advisable to take the intuition from this sort of fluid model to come up with Lyapunov functions for the stochastic model. That's part of the reason I gave you all that deterministic Lyapunov theory before the stochastic. Because you can solve Lyapunov equations for the fluid model, and you'll find that they're really good approximations for the stochastic. It's magic. I wrote a whole book on that because it was so cool how well it fits. You know, it really is. It's amazing, and that's something that, you know, is often true, that the stochastics don't matter for some things. You know, they matter. Obviously, they matter. I mean, God, this thing's bouncing around. The fluid model doesn't capture that, but a fluid model captures a lot, which we will see over and over again in this course. And the only counterexample I've ever seen is finance. And what's special about finance is the volatility models they have are crazy. I mean, you know, their models, the volatility depends on the state. So if I make x large, n gets large. You know, the variability, the volatility gets big with x. And so then a lot of that intuition is much harder. All right, happy?
So in that case, n is not IID.
No. I mean, it's a function of x, t, and yeah. But it's a Markov. I mean, Markov models. Yeah. All right. All right. Should I write it? I'll write it that way. That's not quite, well, forget, this is more general notation, but I'll explain what I mean. So an M1Q is written in I'm going to write it a slightly different way because I want to emphasize it's sort of a controlled model. UT is a control. First of all, okay, so this is a sort of a general model for Q, where these guys are ID, and the control U is chosen so this thing never gets negative. Okay, so S refers to like a service process, and A is an arrival process. And the M1Q is this very, very simple case where A is this 1 minus S. So S takes on, I'm sorry, ID 0, 1. It's Bernoulli, not plus or minus 1, Bernoulli. This is precisely what we had before. It's the reflected random walk. So RRW, reflected random walk. And you work it out, it's just NT is AT minus UT, which is the same as 1 minus 2 ST. Right? I'm just plugging in numbers. I just replaced A by 1 minus ST. And provided U is this provided the input is what's called non-idling. So U is, am I working on the queue or not? Am I processing or not? This is called a non-idling policy. Right? And this might be the outcome of some optimization procedure. I mean, maybe you've got a server who's working in that queue. Maybe it can't work all the time. Maybe it has to walk over to another queue and work on that. There might be a lot of these queues in tandem, and there's a choice on where do I send this server, to do the job. But here if we're just doing a single queue, almost under any optimization criterion, this will be the best thing to do. Just keep working, as long as there's no complaints from the server. No laborers here, no unions here. Yeah. Well, this stands for Markovian. And see, the real MM1Q is in continuous time. And arrivals come as a Poisson process. Service times are exponentially distributed. And it's only after a really fancy transformation you can map it to discrete time. But I don't want to talk about continuous time, so let's stick to that. We'll call it the MM1Q. All right. Okay, so here we don't, because of the fact that these guys are integer valued, that is 1 and 0, we restrict the state space. Just take x just take x to be the non-negative integers. What's that? RRW, reflected random walk. It was just a, yeah. All right. I believe in saving chalk. Okay. Okay, so what I'd love to do in the remaining 20 minutes is try to Lyapunov function and prove a theorem. I don't know if we can do it. We'll see. So now we don't have to have time to do it now. I'll inflict this in the homework for you later. But you can solve the sort of Poisson inequalities for this fluid model. Take it over to the stochastic model, and you'll find it practically solves the same equation. You know, anything you want. Take your cost function here to be x cubed. Solve the Poisson inequality that we studied. And just carry it over here, stick on the stochastic model, and you'll see you almost solve the same thing. So it's pretty sweet. But we don't have time to do that. Let's just play around.
You mean solve, you mean verify its abilities?
Like the things that Poisson inequality that I gave you for either global asymptotic stability or for getting this average cost bounds. You know, that Lyapunov condition for the deterministic system. If you solve it for this fluid model, you'll find it almost solves the stochastic problem as well. But let's forget that. Let's just try to solve the stochastic problem. So, look at this. Now, we won't have time for any theory. Let's just play with this. So, this has a transition matrix. So what's the probability of going up? Well, you only go up or down, all right? So you go up if that's 1, and you go down if that's 1. Unless the state is 0, in which case you can't go down. All right? So if x is 0, that'll be 0. All right? What's that? What's that? Lambda is a, yeah, so you've taken a queuing course. But I'm going to call it alpha. Oh, alpha is the probability that AT equals 1 equals 1 minus the probability that ST equals 1, which is what I called mu. Okay, so yeah, so in some courses you'll call that alpha. So it's got a transition matrix, and so we can use transition matrices to think about Lyapunov conditions. Okay, so just like in the finite state space case, we will see that provided this drift condition holds, you know, that delta is negative, delta is positive. If I look at the probability that in t seconds, I go from one state x to another state x prime, that should converge to a constant as it did for finite state space Markov chains, as it did for the linear model. Well, instead of a state here, I had a set. And I should say x and x. So any x and x prime in the state space, you lose memory of the initial condition. Where you started, this is where you start times 0. And there's a probability that you're at the state x prime at time t that no longer depends on the initial condition. And this convergence will hold geometrically fast, just like it does for finite state space Markov chain. And we can compute it. In fact, we can compute it. We don't even need assumptions of these guys. As long as these guys are ID, you can actually compute them. We won't do that. It's too complex. In this special case, it's easy. But in general, for arbitrary distributions in SMA, you can actually do it. But yeah. Oh, p to the t. Remember that? Oh, yeah. I mean, remember, that's another definition. Yeah. It's matrix multiplication. I mean, it's consistent, but it's a t-step probability. Yeah. But it's good that you asked that anyway. So remember, I mean, it is equal to the sum of all intermediate states. It is obtained through matrix multiplication, all right? But that's just so tedious. We never need this fact. It may be true that p to the t does mean multiplying a matrix by itself t times, but it's so tedious to use that fact. It's so much more useful to write this. It just is. Just believe me. So we just don't bother with that. So we want to, one, we want to find the steady state, and two, we want bounds or compute Okay, so things like this limit of some cost function of the state, it will be equal to this dot product. But we rarely need to know pi to bound to compute that. Right? We use these Lyapunov techniques, and we get bounds to compute this. And it's much more efficient than trying to compute this huge monster in general. Okay? And so, yeah, so this is typical because you care about buffer sizes. You also might care about the variance of the buffer size. You might want to bound on x and x squared, so you know its mean and its variance. These are the kind of things you might look at. So shall we do it? So let's not do this, I don't think, even though it's really easy, believe it or not. But we might as well get a bound on this guy. Okay, so this thing kind of goes linearly down towards the origin and then bounces around. And let's play around with Lyapunov functions just for fun and see what happens. Okay, and first, let's do something really dumb. V of x equals x. What will we learn from that? You know? Let's just try it out. So maybe I just want to practice. Okay. So we know what PV of x is. Okay, again, I take V, I hit it by P, and then evaluate it at x. So I could do this thing I said before, put brackets around that, just to remind you, you know. Okay, because I'm not doing that. V of x is a number. Okay, it's like matrix. Well, let's write it out. So it's two things. It's either equal to the summation over x prime of P of x to x prime times V of x. But that's idiotic, you know. I mean, you've got to store this giant matrix and think about this giant matrix. You're throwing away all the structure. Just don't do it. Just plug in what that is. Okay, so that is true, but not useful. The second thing is to use this definition, which are completely equivalent, but this is useful and this is not most of the time. All right, so if you have this, and I just say, well, xt plus 1 is just x minus u plus that. And one way to write this is just take the positive part. You know, just write x minus st plus 1, and then take the positive part. You know, because if this is 0, that's 0, so the whole thing is 0. Okay. If this is positive, u is 1, so it's just going. All right. You don't have to do that. Let's actually, some of you look confused. Just write it like that. Where is it? What do I?
Bottom line on the left. XT to the left. That one. Yeah, XT.
No, it's not xt because I'm conditioning on big X equals little x. Yeah, it looks big, doesn't it? Yeah. Okay. Okay. So actually, this is true. This is actually, I take it back. This is sort of more useful because u is just a function of x. And now I can go through and just take expectations. We said the mean of this is what? The mean of st, remember st just is 1 or 0. So its mean is, I think you said it. No, st. Oh, nothing is mean 0 here. It's all moving and, yeah, it's mu. Yeah, because, yeah. And we said that the mean of A was alpha. Yeah. Okay. So we're going to have to keep to this faith-based math for now. What we're going to see is when you have a drift condition like that, it's going to imply something about the right-hand side. And we'll write this down one more time. I can't see it there. I've got dv equals v, pv minus v. All right, that's v of x. Is equal to some function of x. I'm just rewriting this one more time to have something concrete in front of us. What we're going to see is that under very general conditions, it implies that the mean of f is 0. So it turns out getting an inequality is really trivial. That's the thing I said is like the fundamental theme of calculus. If I had 5 minutes, I could prove it for you. I don't have 5 minutes. We'll do it next time. To get equality is harder, but can also be done. All right. So what does it mean in this context? So this pi is the steady state probability mass function. So its sum is 1. So the sum of pi of x times alpha is just alpha. The summation of pi of x times u of x, u is 1 everywhere except 0. So it's a probability that the q is positive, non-zero. And there you have it. We learned something. If you believe this fact, okay, faith-based math, let's accept that for now. Then you can go through and say that 0 is equal to this, and here I'm summing over all x greater equal to 1, so that's just 1 minus pi of 0. And I can go and fool around with this. I get 1 minus pi of 0, which is the probability in steady state that x is greater equal to 1, in steady state with distribution pi, is equal to, take that to go through and divide, it's alpha of mu. Okay. Now notice I could do all this without knowing anything about pi. I don't know anything about the steady state. I do know in my brain that it exists, and I do know that there's some nice machinery that allows me to say this implies this. So there are two, this genius in my brain that I'm using. Okay, but once I bestow that genius upon all of you, you can get calculations like that without knowing anything about the system at all, practically. Did I use the fact that that A took on disk value 0, 1, or that A and S were independent, or dependent on each other in this way? I used almost nothing about the system to get this this conclusion that the probability that the state is equal to 1 is equal to rho. Rho is called the load factor again. The arrival rate over the service rate. Okay, so I get this conclusion with almost no statistical information at all, just first moments of this arrival in service statistics. That's what makes this approach so powerful. And trying to compute pi is so fragile. You can almost never do it. Incredibly complex, and you lose all insight. Is this clear? I love it. Most of you look like you're awake. It's awesome. So how do you think I would try to get a bound on like the the steady state Q size? What V would I choose then? You can kind of imagine, right? Here I took a linear function. So what do I do? Take an exponential, log? Nope. X squared, all right. I'll put these brackets in just a little longer. Okay, I know time's running out. Yep.
Sorry, can you repeat the main lesson we learned by the last example, setting v of x equal to x?
Well, we found that PV was equal to V minus F for some F, and the F turned out to be mu times this U of x, or minus mu times mu of x plus alpha. Okay. And you will learn that implies, under very, very general conditions, that the mean of f is 0. There are counterexamples, but very, very generally, it's true. All right? And ridiculously generally, it's true. All right? And so once you do that and you unravel what this means, you get a formula for the probability that the Q is non-empty. All right? And so now we repeat, you know, and we work out this, and you can see it's a little bit tedious, but that's okay. Okay, so we all know how to square something. We get, if I take this whole thing squared, let's just take this squared plus that squared, and then the I mean, it's awful because there are 3 terms, right? So when we square it, we get all these cross terms. But let's just take 2. I've got x squared plus 2x times minus u of x, st plus 1 plus at plus 1, and then plus the other term. And that looks sort of depressingly exhausting. But it's not so bad. It's not as bad as it looks. So first of all, there's an x squared term, right? Right. Now this looks scary because I've got x times u of x. Well, what's x times u of x? X times u of x is x. No need to say more. If x is bigger or equal to 1, ux is 1, x. If x is 0, the whole thing gets canceled out. So we can ignore that term. That's really lucky. This, you got to square it out, unfortunately. But luckily, u squared equals u. And a times s is 0, right? Because either there's an arrival or there's a departure. So the cross term is 0. Okay, so you think I cheated all over the place, but I didn't. A squared is a, because a takes on value 0, 1. S squared is s, it takes on value 0, 1. So if they had different distributions, I'd have to look at a squared and s squared. So the second moment of the arrival process and the second moment of the service process would come into play. But I'm looking at the simple M1Q, so unfortunately you can't see the importance of the second moment of A. Kind of regret that. Maybe I'll make you do it in the homework. So if S is still Bernoulli, but A is anything, you know, you can still go through this whole exercise. All right, done, right? It's all linear, right? So I get this is equal to x squared. And you see I cheated here. I flipped these and put a minus sign. It's because I'll have alpha minus mu, which we assumed is positive. And done. We have this whole monster is my minus f. And you see that inside of f of x is x, the thing I cared about. Now that annoying gain there, I'll put a prime here, how's that? So it's a different, if I divide through by 2 mu minus alpha, then I get my, I can make this be just x by itself. Okay, and then this other term's bounded, just take its worst case. What's the worst case? It would be mu plus alpha over 2 alpha minus mu. All right, now so you can get a bound, you know, which is a bound we'll need this later on. All I did is I took and I divided every single term here by that coefficient. That's one thing I could do if I wanted to get a minus x here. Forget that. 2, 0 is equal to the summation over x of f of x times pi of x. And we'll learn something. So I've got my 2 alpha minus mu x. And then I've got my u of x, or minus these terms, because this is minus f. Right? Okay, so the first term, summation over x of pi of x, x, is what I mean by the steady state mean of c of x. I'll put a pi there to emphasize that that x is distributed according to the steady state. All right, summation of pi of x times x. I just mean that that's a steady state cost. I said c of x equals x. And then we have, that we already worked out. That was 1 minus, this was rho? Didn't I call it rho? The summation of pi of x times u of x, that was rho, alpha over mu. I'm getting there. Well, if you shuffle this around now, what do you get? I get alpha over mu, because that was just, we just learned this, right? That the summation of pi of x times u of x was alpha over mu. All right? And mu is the constant, comes outside. And there's a minus sign around the whole bloody thing. I forgot about that. See, there's a sum there and a minus sign there. So those cancel out. I get a 2 alpha and a 2. The 2's cancel out.
That should be mu.
Where? Oh, yeah. Thank you. Sorry, everybody. Alpha minus mu. Alpha minus mu. Mu minus alpha. I flip the sign. And what do you get? You get alpha over mu minus alpha. Unless I made another sign error. Negative. There's a sign error somewhere. Oh, that should be plus. That should be flipped. Fuck. Yeah. If this is minus f, there's a sign error somewhere. Isn't there? Somebody help me out. Let's see. Where's the sign error? That's positive. That should be alpha. There's a sign error somewhere. Because I shouldn't have flipped things around. You see when I put the a minus s, I put a minus sign there? That's not right. I should have had a plus sign there.
I think so, yeah.
Yeah.
Now look, it's a minus s, you know? So a minus s. I meant to flip these around, and I forgot to. It's okay.
So that's a minus 2.
So right here, there's a minus sign here. And that's good, because I really want to bring this to the other side, because mu is bigger than alpha. The service rate is bigger than the arrival rate. Rho, alpha is less than mu, rho is less than 1. And so you get, without any thinking at all, you get that the steady state mean of the Q size is alpha over mu minus alpha, and if you, you get the rho on top. And if you divide the top and bottom by mu, alpha over mu is rho, you'll get rho over 1 minus rho. Okay? So as rho gets closer and closer to 1, the steady state Q size gets bigger and bigger and bigger and blows up. All right?
How did the sign error affect the
Didn't,
prime wax?
not at all. I see. I knew this was positive. I knew I had to normalize by saying positive. No, nothing's wrong here. It's all fine. No. Disbelieve me. Okay? All right. So you can imagine, if I wanted to get bounds on the second moment, the third moment, the fourth moment, the fifth moment, I could go through and do this and do the same thing. And unfortunately, again, you could do it even if A had an arbitrary distribution. You would just end up with higher moments of A needed the calculations. I guess they're waiting to get in. That noise is disturbing. Okay, so that's another example. Again, if the homework due date is a hardship, let me know. If nobody whines, then I'll just assume it's due Thursday. And theory next time to justify some of these steps.